Okay, gentlemen, today we're going to look at even and odd functions. So I'm first kind of going to look at our functions from the async 2.11 that we looked at the other day. So looking at slide 3 to start, we can see that this function, which you had to describe, we notice a kind of a symmetry here, where my graph goes through the origin, it goes through 0, 0, and then it's the same in one quadrant as it is in the opposite quadrant diagonal from it, so quadrant 3. Right? Where I'm in quadrant 1 and I have this little hump, and then I'm an asymptote horizontally to the right, and then on the left I'm upside down but a hump and an asymptote to the left. Right? So these are symmetrical. This is a symmetrical graph. We call this symmetrical through the origin because it's like flipped down and flipped over, so it's kind of reflected twice, if you will. Okay, and this is one type of symmetry. The other type of symmetry would be looking here, where this does not go through the origin, and it's not the same in quadrant 1 and 3 or 2 and 4, but where is it the same? Right down the middle, if I were to fold this graph along the y-axis, I would have the same function on the right as I do on the left. I have this hump in the middle, right by like -2, +2, right? This little hump in the negative y area. Same on both sides. And then on the top, up above positive y, I have this L, these like horizontal vertical asymptote things that are exactly at the same value. We know the horizontal asymptote keeps me the same, and it looks like I bend at the same areas. This graph is symmetrical. If I fold it left, right, it'll match up perfectly. So let's take a look through a couple of these functions. So I wrote down a lot here, and we're going to kind of zoom out and look through all these functions. So obviously x squared we know. We know what that looks like. It happens to go to the origin, very nice, and then it's the exact same on the left as it is to the right. If I fold this graph down the y-axis, I have the same on the left and right. If I look at x to the fourth, we see it's kind of just a flatter version of a parabola, and it just looks a little skinnier. But it's the same. Again, same thing. If I fold my graph down the middle, same on the left and right. If I look at x to the 6th, just again another flatter version of the same, where I'm symmetrical on the left and right of the positive y-axis. It doesn't have to be positive, but in this case it is. What about x to the 8th rather? Again, just another flatter version of a parabola. These are all the same. Again, symmetrical around the y-axis. It happens to be in positive y, but it could be anywhere just as long as I fold down the y-axis and I get the same thing. If I look at all three of these, you see I'm just kind of getting x to the squared is the widest, and then kind of is the most curved bottom, and they just get more flat and more skinny, or more asymptotic, right? It kind of goes up. But all of these are symmetrical around the y-axis, symmetrical through the y-axis. What do all three of these, or four of these, have in common? They're all even powered, and those are symmetrical over the y-axis. What about this one, x to the 3rd? We see some stuff in quadrant 1 and in quadrant 3, and the area where I'm in quadrant 1 is the same where I am in quadrant 3. Exactly the same. I'm kind of through the origin. I'm flipped down and flipped over, or over and down. I'm reflected twice. What about x to the 5th? Again, just a flatter version of x to the 3rd. I'm symmetrical, what we would say, through the origin. I'm exactly the same in diagonal quadrants. X to the 7th, again, just a flatter version, exactly the same through diagonal quadrants, 1 and 3. All three of these, you can see, they're very similar versions of each other, and all three of these have odd powers. What happens if I were to take x to the 3rd and pop a negative sign in front? Bam. It reverses, but it's the same. It's the same in quadrant 2 as it is in quadrant 4. So it's still reflected through the origin. What about x to the 5th if I reverse it? Here it is. Negative. Bam. Same thing. It flips. It's still symmetrical through the origin. And what about x to the 7th if I make that negative? Well, first I'll show you it positive. Well, there's it negative, and this was a positive. It just flips. Still, either way I do positive or negative, it's the same in diagonal quadrants. Symmetrical through the origin. What happens if I do that with x squared? Negative. It goes upside down. Still symmetrical. Left to right. It's just upside down. What happens about x to the fourth? Make it negative. Still symmetrical, just it flipped down, and it's still symmetrical left to right over the y-axis. Same with x to the 6th, and then same with x to the 8th. So, what do we notice here? Odd powers are symmetrical through the origin, what we would call odd functions. And then even powers are what we would call even functions, symmetrical over the y-axis. Origin, odd. That's how I remember it. Origin, odd. Even, y. What about this one, or 8? H of x is x to the third minus 2x squared minus 3x plus 2. Well, this has x to the third stuff in it, so that's the first power. That's the leading power, the degree. But then I have an x squared second, and then I have an x, so it has a little bit of both. What is this going to look like? Like a regular cubic function. This is not the exact same in the top right as it is in the bottom left in quadrant 1 and 3, or in quadrant 2 and 4. We can tell that because these 2 points, first of all, they're not the same. So I'm not exactly like kind of switching from increasing to decreasing, have maxes and mins in the same area. They would have to be the same points. Obviously not the same sign, positive and negative, but they would have to be the same numbers, and they're not. So this isn't symmetrical at all. And it doesn't go through the origin. What about 9? X squared plus 2x minus 5. This looks like a parabola, but it's x squared, so it looks like the first thing we saw, except it's not through the origin. It's not symmetrical through right and left. It doesn't have to go through the origin, but this point would have to be exactly on the y-axis, and it's not. So that's not a function. These two h's, 8 and 9, are neither. They're not odd or even. A lot of functions we look at are neither. Some are going to be even or odd, and that provides us with some benefit because we know the patterns that's going to come from their values. Looking at number 10, I have x to the 6th, x to the 4th. Both of those are even powers. The 3 is odd, an odd number. But the power, x to the 6th, and the power, x to the 4th, are both even. If I graph this one, that looks like if I fold it over the y-axis, it'll be the same on both sides. Both those powers are even. This looks like an even function. Looking at this point and this point, there we go. Negative 1.4, positive 1.4. And both of them I have a negative 4. So it's the same y value and the same x value over left or right. And up here, same thing. Same x value over left and right. And then same y value. They both had 0. So this would be an even function. Both powers are even. What about number 11? Our last one. Both powers are odd. The 4 is even as a coefficient, but the power of 5 is odd, and the power of 3 is odd. This looks like an odd function. I'm symmetrical through the origin. Now again, as we saw, like this it has a negative, so now it's in quadrant 2 and 4, but it's also in quadrant 1, positive all the way up, and quadrant 3, negative all the way down. Are those two little switch points from increase to decrease in quadrant 2 and 4 at the same values? Negative 1.549, 5.949, and 1.549, negative 5.949. This looks exactly even. Negative, positive, positive, negative. Same over here. This is obviously the origin, or the x-axis, that doesn't really, you can't have a negative version of 0, but your max and mins are exactly the same decimal. So clearly this is symmetrical perfectly through the origin. Okay, so now that we've kind of discussed it all, we're going to look at this set of notes. And we see here, we're going to start with the first one, which is even, right? Just to keep consistent. Even functions. And as we saw, symmetrical over the y-axis, and that's what it says right here. Graph looks the same. I'll highlight it actually. The graph looks the same left to and right. Right? And we can see here, plugging in a negative x would give me a certain y. Plugging in a positive x would give me the same y. And that's what this is saying. F of x is going to give me a y value, and f of negative x is going to give me the same y value. That's why the negative versions of my functions looked like this, because positive x or negative x gives me the same y value. And we can see that here. Even, symmetrical over the y-axis. Okay, these down here were odd functions. We see that right there, odd. And we see here, this graph looks the same upside down as it does right side up. So what we say is symmetrical through the origin, as we see that right here. Okay, and it shows you, all right, x to the third, this is in quadrant 1 and in quadrant 3, or it could be in 2 and 4, either one, but it's going to be kind of in that diagonal. I say it's in the diagonal quadrants. That's kind of how I say it's symmetrical through the origin. And as it says here, and we kind of saw this in our points, f of x is going to give me a y value, and f of negative x is going to give me the exact same y value but negative. And that's why you're in diagonal quadrants. Positive, positive, negative, negative. You're an exact opposite. Or as we saw, negative, positive, positive, negative, same values. So we see here, negative 3 gives me negative 27, positive 3 gives me positive 27. And that's what we see right here. Plugging in an x is going to give me the y, it's going to give me the exact negative version, and that's what this is saying. Right? And it says here, down here, graphs do not have to be symmetrical. They can be neither. That means they have no symmetry. And we saw that if I have even powers, all even powers, the coefficients don't matter to me. Sorry about that. It will be an even symmetrical function. If I have odd powers, it will be odd symmetrical. It'll be an odd function, right? So symmetrical through the origin. And I'd write this down, symmetrical through the origin. An odd function has all odd powers. An even function is symmetrical through, or I'll say over, actually that's better, over the y-axis. Okay? We also just see down here, the textbook also shows symmetry with respect to the x-axis, right? That's not a function, as it very clearly states over here. But we could, graphs with this kind of symmetry are not functions. Okay, except the zero function, which we don't need that right now. So these are not functions, but it's the same idea where if I plug in a certain x value, 9, I'm going to get out the y value, positive and negative versions. So the same x value is going to give me positive and negative versions of the y value. Not super important to us because we're just focusing on odd and even. Okay? So good luck on your async Canvas quiz that counts as an async assignment.